Leetcode 1857, largest color value in a directed graph. The hard problem, so it requires some thinking. It's a multi-step solution, and maybe relatively to other hard problems, it's not the worst, but definitely takes some time to even come up with some plausible solution for that. So let's start reading the description. There is a directed graph of n colored nodes and m edges. The nodes are numbered from 0 to n-1. So already first sentence, and we have a lot of information, and also to even understand what they are talking about, we need to have some prior knowledge about graph theory. So first thing, there are directed graphs. So either we have directed or undirected graphs, and in undirected, if we go from A to B, we can also go backwards, but in a directed, every edge, so every connection between two nodes has a direction. Yeah? So if an edge goes from A to B, then it only goes in that way, and there would be a separate edge going from B to A, for example, if it exists, but that would be in most cases not even a thing that we desire. So let's draw a simple graph, and let's say we have such a situation that there are 3 nodes and 2 edges right now. So let's give them names, A, B, and C. Yeah, and if in the visual representation we draw arrows, then it usually means that the graph is directed, and if there is an edge that goes in one direction, that we usually cannot just assume that there is a way in a reverse direction. But if there was a way, for example, if I also could go from, let's make it a bit thinner, from C to B, then such a situation would be called cycle. Yeah, and that's not really good. Usually that's something that we try to avoid. Yeah, so let's write it down. That's cycle, and let's get rid of that. That's just some confusing stuff, and that's something that we try to avoid. Yeah, because in that case, if we go from B to C, we can go back and so on and get stuck in some infinite loop if we try to traverse our graph one by one through edges. And let's go back. So the second thing, besides the fact that they specify that it's a directed graph, we have colors. Yeah. So those nodes, so the elements of our graph, can store some data. In that case, we store, for example, letters. So each node stores one letter, A, B, and C. And besides that, in certain cases, we want to assign labels, additional labels to the data that is being stored, which are usually called colors. And colors could also be represented as letters, so it could be like ABC, or it could be like a real color. So we could, for example, say that node has a color. Let's even give it a color blue. That one has a color pink, and that one is green. And usually in most cases, we don't want adjacent, so the nodes that have connections to each other, adjacent nodes to have the same colors. That's mostly the constraint that is being given when we are talking about colors. But let's see what's happening here. So yes, so we talked about directed, we talked about colors, we talked about nodes, and there's and edges. So there are simply n nodes and m edges. And the next thing is you are given a string colors. So they are describing the inputs, where colors of I is a lowercase letter representing the color of the ith node in the graph starting from 0 index. Yeah? So let's just write it down already. what we have as an input. Let's put it here. Colors like that. A, B, C, A, and they can be repeated. So each color in that case is a single letter. And the most important thing is that their indices are mapped to the nodes themselves. Yes. So those would be the let's maybe do this, some spaces, 3. And let's make it maybe let's change a color. No, that would be too many colors. Yeah. So let's leave it like this. So those are the values themselves, and here below are the indices which represent the mapping. So the first color A would be the first would be mapped to the first node, and that's how we know which node has which color. And so that's usually what they prefer in those problems, is that the nodes themselves are represented just as consecutive integers, so they can reuse indices in arrays for mapping between the nodes and some kind of information about the nodes, in that case colors. And you are also given a 2D array edges, where edges on index j is a mapping between aj and bj, indicates that there is a directed edge from node aj to node bj. Yes. So that was some Wikipedia article about topological sorting. So small preview of what is coming, and let's write it down here as well. Edges. Let's go for this, and 1, 2. So we will have a list or an array of pairs of edges, and the edges always represent the edges from the first node to the second node there. So if in that list we have pair 0, 1, that means that there is an edge from 0 to 1, and if there is 1 to 2, then there will be 1 to 2. And if you wanted to represent that graph that's here on the left side, we would also have 2 to 1 represented like that. That's more or less what they want. And yes, so those are the edges. And then the next important thing is path. So a valid path in a graph is a sequence of nodes, x1 to x2 to x3, and so on up until xk, such that there is a directed edge from xi to xi plus 1 for every I between 1 and k. The color value of the path is the number of nodes that are colored the most frequently occurring color along the path. Okay. So again, a lot of information. So first of all, what is a valid path? Path is simply just a collection of nodes, and which are connected through edges. The valid path would be simply us going alongside the arrows. Yes. So if we start with A, one valid path is to go to B and then C. Yeah? And this is just a path. Path doesn't necessarily mean that we go through everything in the graph. Yeah. There could be also a path that spans across the whole graph, but a path is just sequence of nodes that we visit, and doesn't necessarily mean that we have to visit everything. And there are valid and invalid paths, and here's a constraint for that. And then they want us to find the color value. So as we go through the path, we will visit different nodes, and we simply want to find the color that is occurring the most in a given path. So we have to explore multiple paths. For each path, we have to find a color that occurred the most during our traversal of that path. And from all possible, we have to find the one that has the highest number. Yes. So in that case, for example, in the case of this path A, B to C, here everything has the same color. Yeah, but if I change that to blue, then we would have, if we go from A to B to C, we would have blue 2 times. So our color number in that case would be 2. That's what they mean by that. And that's more or less it. Now return the largest color value of any valid path in the given graph, or -1 if the graph contains a cycle. Yeah, so if you have a cycle, which we already discussed shortly, then we cannot, we should not proceed. We should simply return -1 at that point. And here is a simple example. So we have colors A, B, A, C, A, and edges from 0 to 1. So here goes 0 to 1, then 0 to 2. Here is the second edge, then 2 to 3, and 3 to 4. So everything seems to be okay. And the colors A for the 0th node. So A in that picture is red. B for the first node, which is violet. Then A again, okay, which is again red. Then C, which is blue, and A again. And what is the output? The output is 3. So if we choose the path 0, 2, 3, 4, then we would have color A, or the red color, occurring 3 times. And that's the highest possible value that we can have for that graph. Okay, and the second example is an example of a graph with a cycle. So there is an edge, and the edge goes from the node to itself, and that of course also creates a cycle. So we will draw a cycle that goes from one node to another, and then there's another edge which goes in the opposite direction. That creates a cycle, but we can also have smaller cycle from the node itself. If there's an edge from the node to itself, then that's also a cycle, and in that case we also have to return -1. Okay, so let's write down what we have to do. We have to find the maximum color path. So let's write it down as our goal. Maximum and not even the path itself, but just the number, what we are interested in. So of course, as with everything connected to graphs, we have to somehow traverse them. So is there any other goal that we have to think about? Yes, detect cycles. Before we proceed with explaining the algorithms, so let's just write down everything to keep in mind, because it's easy to get lost in those details. So detect cycles, and that's it for now. I think we can put it in some frame so it stays with us. Let's make the background transparent and leave it like this. So that's our goal. We can get rid of that graph that was just created for the purpose of explaining what is a cycle. And now we have to somehow find the path that is valid. So what do you want? Traverse. What options do we have? BFS and BFS usually. So I'm just writing down my thoughts, and let's think about this. So with BFS and DFS, usually it's they have some differences, but usually it's good to use them if we have some clear starting and ending point. But in that case, or if we just want to traverse the graph once, but in that case, we have multiple possible paths. So where is our starting point? If you will be starting everywhere in every node, and trying to come up with all the possible solutions, that will very easily get very complicated and will for sure not be the optimal way to solve it. So because it's not an undirected graph, but it is a directed graph, we can use some other algorithms. And mainly we can think about topological sorting, which I was trying to decode just before this video. And important thing about topological sorting is that most algorithms operate on the directed acyclic graph DAX. Yes, and in our case, we can have cycles. So they can provide us with such an input that will contain cycles in them. But if a cycle occurs, we just need to return -1. So we can simply disregard those graphs. Once we detect the cycle, we simply return -1. So we can proceed with a simple with normal topological sorting algorithm, and the most common one is called Kant's algorithm. And in that case, it could give us some better optimized approaches. So topological sorting might be faster since we have directed. Enough. Yes. And we just make this. Oh, so you cannot just mark a single word with a different font color. Okay, so let's leave it like this, and let's think about how can we start and how such a sorting would work on our algorithm. And for that, the best way usually is just to copy the example that they are providing us with and work on that until we have more or less the algorithm in words, and then translate it into code. So let's start with that, and let's copy that input. And let's remove that stuff that we had before. That's our input, so we can try to withdraw it. We have, by the way, we can already see how many nodes we have. So there is 1, 2, 3, 4, 5. The 5 elements, 5 characters in the string, and that tells us that there will be 5 nodes. N equals the length or the size of colors, and in that case, it's 5. And let's make it bigger. 0, 0 goes to 1. So there is an edge here. Here, 0 goes to 1, and 0 goes to 2. There is another edge below. and 2 goes to 3, and 3 goes to 4. And we have the following colors. So A is mapped to 0. And so we can represent A as red. Then the B is mapped to 1. And we can represent it as green. Then again A. Then again, then C is for node number 3. And let's use blue, for example, and red. So the first question, what coming up with when trying to construct a path is where do we start? Is how to know where to start. And is there something that we can already observe on that graph? For example, if I start here at 2 and then proceed to my neighbors, which are only through the edges that are outgoing from my node. In that case, it would be only that edge going to 3. If I start here and then go to here and then go to here, I have a path. And in that path, I can see that the red color is occurring 2 times. But is this the smartest way to do it? Maybe not. Why not? Because if I start from 0, then I can go also to 2, 3, and 4 and construct such a path, which would contain already that other path that I explored. Yes. So in the best possible case, we would never want to consider paths which are the sub-paths of some other paths. We only want to have those most complete paths possible. And for that, we can start sorting our graph by the number of incoming edges. Yeah, so there's another term in degree. I don't know if this is one word or are they separate. Let's go with it. No. Here in gigs for gigs they claim that it's okay. Here also in degree, so it seems to be a single word. In degree. And what does in degree means is a number of edges going into gig. And if in degree of my node is 0, then probably that would be a good starting point. So for that, I have to somehow find out the in degrees of each and every node, and then start exploring the paths for all the nodes which have in degree of 0, and those would probably yield the best possible paths, and so on. Yes, so that CAN algorithm and topology curve sorting for that case would be exactly this. So we would compute in degrees for every node, find which ones have in degree of 0, start at them, and then proceed with all their neighbors by decreasing the in degrees of each neighbor by 1, since we already explored one node, and so on, and up until we have completed the graph, or we detected an edge, not an edge, we detected a cycle. And in that case, we would not explore all the possible paths. We will just try to explore the best options and have more optimal approach than simply traversing through BFS or DFS. So let's write it down. So steps, yes. Now let's put it here, or maybe just scroll a little bit down to separate some thoughts that we have from the actual algorithm, and let's try to write them down. If they will be incomplete for some reason, then we will try to adjust. So let's put it here. First, find all nodes with in degree 0 for each of them. Find corresponding color and increase or increment some counter corresponding to that color. Just maybe not to repeat corresponding to many times, just color counter. And how that color counter can look like. Could it be, for example, a single variable? Probably not, because just some individual number. Probably not, because we have, first of all, multiple possible colors, all the letters of alphabets. Between A and Z, there's 26 letters. And also we have many nodes. So for each node, we need to find the best, so the most occurring color for that node along any valid path. Yes, so that means that we have multiple possibilities or multiple counters that we have to keep track of. So 26 times n, to be precise. And that we can maybe already write down and just here on the side, so we don't forget that. So how many options there are? We can have the following columns: A, B, C, D, and so on. And we can also have the following rows: 0, 1, 2, and so on. Yes. So, like that. Let's make it like this. Let's put here a line, and let's put right here. So for each combination of node and color, we need to keep track of how many counts already have occurred. So at the very beginning, we can simply initialize that with zeros. Move. Yeah, and let's put some zeros here. 0, 0, 0, and 0. Zeros here, and so on. And we have always the same number of columns. So it could also be flipped, yeah? But let's put it like this. We can have 26 columns, since there is 26 letters between A and Z, and those are our colors or labels. And this depends on the number of this depends on the input. So on the size of the colors string that they give us in the input, depending on how long it is, what's its size, then that many rows we will have. And we have to keep track of all of that if we want to have correct result. Here. And we can give the structure some name. So let's call it color count. That's our color count. And put the name here, or maybe move everything a bit below, so we have a bit more space. That's our color count. So here is the algorithm. Here are some additional structures that we will have to create. So we already talked about in degree. We have a color count, and let's proceed with the steps. So what next? Then we will need to proceed with all the neighbors. Update their counters as well. And decrement their in degrees corresponding to the source. And since once we proceed with a given node, the in degree value will change. Yeah, since we can mark given node as visited like that. And that's it. And stop when there are no more nodes with in degree 0 that haven't been visited. And in case we didn't go through each node, we have a cycle. So in that case, we will have to return. We will have to return -1. So those are all the steps. To be precise, one more thing that we need to discuss is how to get the neighbors, since the data, the input data is given in such a way that we just have the edges, but how can I find, and I'm not even sure if they are sorted. Yeah? We just have edges. Maybe they are sorted, it can be checked in the constraint, but either way, we don't care about this, since if you want to find all the neighbors in that raw form that they given us, we would have always to look through each and every element of that structure, which would be an ON operation, and simply find for each element we would have to find like the first element of the pair, and the second would be our neighbor if the first is equal to the one that we are looking to. But we can transform that to adjacency list, which would give us the search in O1 complexity. So from that we can build or transform to the list for past neighbor retrieval. Yes, and maybe let's just write it down. How would it look like? So in that case, let's copy it down here. JSON list from that would be the following. For index 0, we will have 1 and 2. Then for index 1, we have an empty list. And for index 2, we have single element. And for index, we have single element 4. And for index 4, we have nothing. Yes. If we transform the list, we get something like that. 1, 2, then empty, then 3, then 4, then empty. And if I now want to find the neighbors of element 2, for example. Then I have O1 operation, just give me the neighbors, and I don't have to look through everything again. It will just give me back this list with 3 inside. What would be it? That's more or less it. So the core of our algorithm is operating on those indices of 0 and sort of sorting like that, but we will not have a sorted structure in the end. We simply use that sorting, or we take advantage of it to do the traversal and to explore different paths. So the sorting itself proceeds through all of that, since we always update the integers and we continue with taking new nodes, but we will not by the end have the sorted version of that algorithm, of that structure. I mean, in any way, we just use it kind of as a traversal. And that's more or less it. So now we have to try to convert those steps, which are loosely formulated, to some hard form, which is code. We have a lot of structures, as we discussed. So adjacency list, we can just call it adjacency. Let's leave it like that for now. Just write down everything more or less that we talked about, and then we will fill out the blanks. So we need an adjacency list. We need, first of all, n, which will be the number of nodes that we have, which we already agreed on. We can take from colors. So they provide us one color for each node, and the index of the letter inside the color strings corresponds to the node. So that is our n. And then we also need our in degree, which is a single word, as I learned a couple minutes ago. We also need the color count. We will also need a queue to enqueue the elements of to enqueue the nodes which have in degree of 1, in degree of 0, all nodes in degree of 0. Here will be to the list every combination of node and and color. And the heart of the algorithm, once we prepared all the structures, will be that sort with cans algorithm using that queue. In fact, the queue itself also belongs to that, so we can also put it here. Yeah, while we still have elements in the queue, we will do something with that, and by the end, we will return a result. So for the result itself, we also need a variable, so max. Either we can call it result, or max colors, or max number, or something. Maybe max color will be the most appropriate. We can start with some very small, and as we process our queue, we will be updating it, and in the end, read. Okay, so let's start maybe with building our stuff. So we need to build the adjacency list to retrieve the neighbors. We need to build the in degree, and we need to build a color count. Let's create some functions for that. Build graph. Can set n, edges and n, and how to proceed. So the graph will look like that. At the end, we return the graph. has n lists or underscore in range n. Is that to the list of lists. Each element of the outer list is a row or a list itself. It's our graph, and we can traverse the edges or iterate through edges by simply unpacking the source and destination in edges and updating graph of source, append a new destination. And that's it. That's our graph. Ranges n. And we can do a very similar thing for the in degrees. Build in degrees. Just that we don't need a 2D element, we just need one-dimensional lists, just a fluff list. And so for source and destination, we will update. Let's not call it graph, let's call it in degree. We will update our in degree of destination. Yes. Every time we found a new place which leads to a given node to our destination, we simply increment by 1 and we start everything with 0. And that will be the second. That will be our second structure. And here we can maybe do it in a single line using list comprehension. Or no single. Well, it could be a single line if I didn't break it, but we need a single list comprehension. We need to have 26 columns and 26 columns and n rows. Yes. So here for e underscore in range 26. Sorry, a better way would be 0 times 26 or underscore in range. That way we will have 26 columns and n rows. Okay. That's already something. And now we have the Kant's algorithm already. So we simply first can create a list and then map it to the queue that we need to import from collection, import the queue, and this will be node in range n if in degree of n equals 0. Okay. And now we go inside and we pop from our queue the first node, and then we need to do two things. We need to count the color for that node, or increase the count for that node, however you want to word it, and then we need to propagate to each neighbor. Yes. So the counter, our color counter, how did we call it? Color count is a 2D structure. So we need the row number and the column number, and the row number is of course our node, and the column number would be our color, which we can take, which we have to map to like a number starting from 0 up to 26. So we simply can take the letter from the string colors by doing this. Then we can convert it to a corresponding ASCII number and decrement the number for A. Yeah, so in that case, the A would be 0. If here we had A minus A would give a 0, and B would be a 1, and so on. Yeah. So in that case, that's the way we can retrieve the column index and just a column. Yeah. Node is our row and color is our column. And we can increment it by 1. Yes. And we have already created a structure of max color. So max color, whenever we increment the color count for a given node and color, we simply take the maximum from this and from the previous color. That's it. That's it for the count of the node. And now we need to go to the neighbors. And we already said that we will use adjacency list. And it's a list, so square brackets. Yeah. That's how we can retrieve easily. Look, so easy at this point to get the neighbors. If we didn't create this adjacency auxiliary structure, then we would have to go through each element every time of edges and look for the edge that is starting with our current node and so on, which would be very messy. So adjacency list helps us a great deal at this point. And for each one of them, we have to propagate the color, which gets a bit tricky. So we have to go again through each color in the range of 26, which is between A and Z. And for each one of them, we can update. So color count of neighbor is the maximum between the neighbor and our current color. Is the case, and the next thing is that we can decrease the in degree since we have already processed the node that is coming into you into the neighbor, so we can decrease the in degree of neighbor by 1. And if in degree of neighbor equals 0, we can append to our queue. Don't know if queue has also append, I think yes. Either append or enqueue, however it's called. The neighbor. Yeah. The last thing are the cycles. So we can introduce another counter, and now I'm thinking about how to call it. Maybe processed. Yes, and each time we process a node, we increase it by 1. And by the end, we check if we process everything, if it's equal to n, yeah, then we processed everything exactly once, and otherwise we return -1 because And the opposite situation, if we didn't process everything, that means that there was a cycle. We don't want a lot of stuff happening here. Let's try to run it first on the given test cases, else and if, and of course there could be something. Which I misspelled or something like that. Else after expected else. Yes, I think I know. I used some wrong syntax. So it should be node for node. That would be correct syntax for list comprehension. And here, spelling error. Again, index out of range. Did we create in degree already? Let's copy that to PyCharm. And let's debug. So let's open some Scratch. Call it new Scratch. And let's use that input. Press from typing inst. Colors and edges. Let's pass our stuff here. And let's see what's happening at this point. I see already. So, but let's go. Let's proceed with that. No, sorry, not run all. I meant debug. Start debugger. This is a method, so yes. So let's try to evaluate this expression. With index out of range because n is our size. It's not the node. So if we change it to node, then it should be correct. Perfect. Okay. Let's change it here and let's copy it back. And run again. Now it's accepted. And let's submit for all the test cases. Not bad, with 60%. We can, I think, optimize some things here and there, but let's take a look. There's some easy stuff to optimize. That's not. That probably can be done faster than a normal loop. I wonder if we could use a comprehension here. Yeah. Okay, so we can think about, of course, some optimized solution, but more or less, that's what we wanted to present here. And it's a hard question, first of all, so a lot of things that we discussed, I think it's really worth taking a look into if you are studying Leetcode.